Hello, I'm Sonuli. Um, I graduated last year. I was a PhD student when I was working on this work last year. Today's topic is a case study on parallel HDF5 dataset concatenation for high energy physics data analysis. So I'm going to briefly explain the background first, the high energy physics workflow and data storage. In high energy physics, a large amount of data is generated from the scientific instruments like detectors, neutrino detectors. And typically, because of the grid-oriented environment, a large number of files of moderate sizes are stored. And to better use of them, it is actually better to have a smaller number of larger files. So in this case study, we will consider how to aggregate the data across a large number of such HDF5 files. Specifically, we will consider NOVA experiment data, which consists of hundreds to thousands of HDF5 files. The total raw data size is order of terabytes, and the compressed files take up like 35 gigs to 213 gigs, quite a large amount of data. We will explore a large number of HDF5 features and how to use them, better use them to aggregate the NOVA data on HPC systems. NOVA experiment data, it's a NUMI off-axis VE appearance NOVA experiment, we have two detectors. One is near detector and the other is far detector. This data is generated at Fermilab in Illinois, and near detector is there, and the far detector is in Minnesota. So on the right side figures, it shows how it works. A beam of neutrinos is generated at the Fermilab, and the beam is the beam goes through the detectors, and some properties are recorded at the detector side, and it results in having a large number of HDF5 files. Here's the statistics. We have two different sets of files, near detector files and far detector files. The near detector data set have 165 files. Far detector files have 6,400 files. Each file has a large number of groups and data sets as shown here. We have two types of data sets, 1D data sets and 2D data sets. 1D data sets are mostly empty actually, but we keep the metadata for these empty data sets because domain scientists may need these data later. So the raw data size before compression and after compression show large difference, which means the data is highly compressible. And noticeably, the metadata takes up a large amount of larger size, 11 gigs for ND files and 100 gigs for FD files. Metadata takes up so much space. So everybody should know HDF5. I'll skip it. So the workflow, parallel data aggregation, we define these aggregation steps like this. We are given F files, and we concatenate all individual data sets across these F files and write it into a single large output file. This workflow consists of 5 steps. We first evenly distribute all the input files to the P processes and collect the aggregate dimension sizes and the data types of these D data sets. Then we create a single new large output file and create all the data sets using these aggregated sizes and output data types. For each data set, we read the data set from all the assigned input files and then into the memory space, and then write it into the output file at once. We will be running this concatenating program on Cori, NERSC Cori supercomputer. We use the Xeon node, the CPU node, because it has the larger memory space. And the parallel file system on Cori is Lustre. We use the file stripe size 1 megabyte and stripe count is 128. We used this specific setting and fixed it during the whole experiments. All right, so metadata IO. We first need to collect the metadata from all the input files, as I mentioned just now, data types and array size at least. So for Nova files, collecting such data takes much time. We have hundreds to 1,000 files, and each file have thousands to 10,000 data sets. So it's not negligible. So we have two design options. One is on-the-fly I/O. We can read the metadata on the fly while the analysis program runs, or we can open all the input files in in-memory I/O mode, and the metadata will be automatically located in the memory space in advance. So we compare the performance. Actually, we are making a trade-off between the memory space consumption, memory footprint, and the metadata I/O time. On the fly, if we use only one node, it does not make sense. It takes more than an hour. I know an hour. Yeah, and in memory I/O, it becomes 1 minute, and they are scaling well. But we can see the memory I/O significantly improves the performance while spending a large amount of memory space. And the metadata write, we need to write the metadata to the output file when we are creating the new data sets. We have two timings here. Here's the timing breakdown of the creating output file data sets. Basically, they are not scaling well, but the most of the time, the left side shows them on-the-fly creation. The right side, no, sorry, I was confused. So we have two options here too. One is we can open the output file in POSIX mode, and the other option is we open the file in MPI IO mode and create the data set in using collective IO. These two options have similar execution time because HDF5 triggers fill in operations internally when we are creating an empty data set. That's because we are creating the data set that is chunked and compressed. Under this situation, HDF5 internally write down some fill-in value, predefined fill-in values in advance. That makes these timings. So no matter what option we use, that operation takes a certain amount of time, and we can see that these two options do not show any large difference. Chunking and compression also matters. HDF5 requires users to use chunked layout for data compression. As shown just now, our data is very large and highly compressible. So that's the reason why we consider HDF5 as an IO library for this case. We need to use the compression feature. And that means we also have to use the chunked layout. We have 4 charts here. The left two shows the ND files, the right two charts shows the FD files performance, timing breakdown across different chunk sizes. We tested from 256 kilobytes to 256 megabyte size for ND files. As you can see on the left two charts, one is small 1D data sets. The second one is large 2D data sets, timing breakdown. Basically, the larger chunk size gives more expensive data transfer cost across the processes because HDF5 makes each process deal with one whole chunk, one by one. So every process has its own chunk. If the processes have partial chunk, they have to transfer each other so that all the processes have whole chunk. So because of that, if the chunk size is too large, we may have more expensive communication cost. On the other hand, if the chunk size is too small, metadata, the amount of metadata increases, and the metadata operation time will increase. And also we can expect a shorter compression time. These are the insights we got from these chunk size experiments. And for the FD files, 6,400 FD files, each file is smaller than ND files. So they have these two sets of files show kind of different behaviors, but similar. So larger the chunk size, we have more expensive communication cost, while cheaper metadata handling cost. Yeah, there is also the metadata caching feature in HDF5. We have a large number of data sets, 13K to 16K. So caching metadata would be a good idea. The default size of the metadata cache size is 2 megabytes, and it automatically adjusts based on the hit ratio. Instead of it, we increased it to the maximum allowed size, 128 bytes per process, and turned off the automatic adjustment. Under this setting, we could improve the overall metadata handling performance by 25%. All right, I finished the metadata IO part. All right. Okay, the parallel read. We have been talking about the metadata handling. Now we'll talk about how to concatenate the actual data. We are given a large number of files. We have also two design options. All the processes can go through all the data sets one after another, reading the data set using the MPI collective IO. The other option is we distribute the files to all the processes evenly, and then they independently read the data sets using POSIX IO. We collected the performance timing breakdown of these two, actually three design options. DP is the data set partitioning, which means all the processes go through the data sets one after another using MPI IO mode. FP is the file partitioning. We distribute the files to the processes and they independently read the data. FPIM means the same file partitioning using in-memory IO. As you can see, the file partitioning with in-memory IO shows the best performance. Of course, we will be using the more memory space. The reason for ND files is mostly because of the decompression time, and others here means the metadata handling. So metadata cost goes down and decompression cost is almost the same. For the FD files, excuse me. So the metadata handling cost is reduced dramatically when we use the file-based partitioning because they don't do any, the total amount of metadata each process has to handle is proportionally reduced in file-based approach. So in this specific case, we found that file-based partitioning is better. Parallel write. We finally have to aggregated data. We have to write the aggregated data into the output file. So regardless of which read strategy was used, the parallel write should be MPI collective IO. We don't have any other options. Because the data is distributed across all the processes, we have to write it into a single data set, a single output file. So for likely the left two charts shows the ND files performance, the right two charts shows the FD files performance. So interestingly, when we are writing the data, compression takes up most of the time, both data sets. So compression, the chunk size is important, And also for the small data sets here and there, the writing time takes up much time, and also the read takes up a certain amount of time. The read here means the data, the basic IO strategy of HDF5 is read, modify, write. So even if you want to write something, if you're writing a part of the chunk, you have to read the whole chunk first and then modify it in the memory space and then write the whole chunk. So because of that, we also performs a certain amount of read. So these are the key observations in this case study. So finally, the end-to-end performance evaluation. We could successfully scale up this concatenation, data concatenation for HDF5 data analysis using up to 1,600 processes, 400 nodes on query. And the entire data set was well concatenated in order of minutes. Yeah, summary, this work is written as a journal paper. It's under review right now. So our lessons learned from this case study can provide good guidance for any kind of applications that have similar data characteristics. All right, this work has been supported by DOE grants, and yeah, that's it. Thanks so much. Any questions?
Thank you. Yes, I have a question, and I believe there was a question in the chat or suggestion. Have you tried to disable rising field values when you were creating data sets?
You mean the zip level?
You can disable writing field values to the data sets. There is an API, H5P set field time to never.
Right. Yeah, we actually tried a couple of different compression levels. Yeah, I didn't include that result here.
It is not compression; it's field time. So by default, when you create,
right, that makes sense.
I think.
Yeah, then another question, and maybe someone can help me from the HDF group. I don't remember. Do we have APIs to indicate that we will be overwriting the whole chunk, so there is no read operation is needed, or it's one of the optimizations we still need to do?
We don't have any APIs, but if you're using compression in parallel, we do detect if you're overwriting the entire chunk, so that will skip any reading of it. It should only be when you're doing partial writes to a chunk that we have to read it.
Yeah, right.
Also, have you played with, there is an API to aggregate metadata in, have allocations for metadata sizes. So you will aggregate metadata and will write it only when it reaches the specified size. I don't remember API from my head immediately, but it's metadata block size, something like this.
Yeah, right. I believe that's exactly what we tried, the metadata cache size. And 128 megabytes is the largest size. And that means 128 megabytes means the HDF5 will aggregate that amount of metadata and then write it once.
Okay, so
yep.
You use that. Okay.
Yep.
Interesting, thank you.
Sure.
So now I have a question about selecting the chunk size.
Yep.
It seems you tried a few chunk sizes, but is there any model that you could come up with what chunk size would give best performance for a given?
Yeah, that's a good question. Actually, it makes trade-off. So we found that for both data sets, we found that 1 megabyte to 4 megabytes, this specific size generally worked well because that makes a good trade-off between the compression cost and metadata handling cost. But that depends on the data set characteristics, like what's the size of each data set and the degree of compressibility, something like that. So yeah, in this case study, we suggest 1 megabytes or 4 megabytes.
And I have a question about your compression. Which compression did you use?
If I remember correctly, we used the default one. What's that? Yeah, it must be. What's that? We used the gzip. No.
Gzip.
Yeah, gzip. Zip.
Because it looks like your data is very sparse and really compressed as well.
Right.
Right. Okay.
Yeah.
Yeah. Okay. Thanks.